Good evening. Our today's speaker is Georgy Шарыгин, and he will tell us about geometry of the full symmetric Toda system. Gosha, you're welcome.
Yes. So, just a moment, I need to put on this harness. I wonder whether Chagin will come.
Чагин вас слушает.
He's listening to me online.
Ему ему очень далеко ехать, поэтому,
Хорошо.
извинившись,
Ничего страшного.
начал разрешить.
Okay. Just wonder whether everyone hears me okay or not. Is it okay? Does everyone hear me?
Well, please reply, anyone. Can you hear us?
You can use chat. Okay, any case, let us go on.
Well, let us hope
that they do hear us. Okay. So I'm going to speak about the full symmetric Toda system. There exist different ways to introduce it, and I'm going to stick to the most naive and straightforward one. I'll explain what generalizations there can be and how one can reinterpret it in different situations, but I'll stick in my talk to the construction, which is the most classical one. So first of all, let me recall that the usual Toda system, Toda chain, open Toda chain, is the system which is determined by its Lax form. Actually, there are different ways to introduce open Toda chain as well, but I'll stick to the Lax form. We choose two matrices, or we choose just one matrix L, which is symmetric and has 3 non-zero diagonals, A on diagonal, A1 through AN, B1 through Bn minus 1 are off-diagonal elements, and zeros stand on all the other places. Then we introduce its naive anti-symmetrisation, M of L, which consists of taking the upper triangular part of L and subtracting the lower triangular part of L plus and N minus. So in more explicit terms, we should delete the diagonal, preserve the sign of the terms above the diagonal, and change the sign of the terms which stand below the diagonal. And the Lax form of this equation is L dot is equal to the commutator of ML and L. This equation was motivated by the study of the Hamiltonian system with Hamiltonian H of PQ equal to the sum P square Pi squared divided by 2 plus some exponent of Qi minus Qi minus 1, sum from 1 to n minus 1, and here the sum is from 1 to n. And the coordinate change which gives us this kind of system is prescribed more or less by the condition that this should be squares of B, and this should be squares of A. The Hamiltonian in that case translates into the square the trace of the square of L. It is a bit more interesting to describe the Poisson structure, the Poisson bracket, in terms of A and B. We can do this explicitly and obtain a formula. Well, I don't remember it very well, but it's something like A I with Bj is equal to trace L square. Oh, sure. Okay. Sorry. Yeah, that's my mistake. Sure. It's something like delta I j b j minus delta I j minus 1, something like that, b j minus 1. Well, I'm sorry, I don't remember this very well, but we will not need this in the nearest future. Just something to make sure that this is Hamilton system. This is also Hamilton system. And so I'm going to generalize the system a little bit, and I'll speak about this generalization ever since.
A's commute with A's.
Yeah. All the rest, all the other commutation relations vanish. Okay, so now the full symmetric Toda.
Just a moment. Can you say a couple of words how it relates to the mechanical model with these masses?
Yeah, here it is. Here is the usual Hamilton system where the Poisson structure is given by the standard formula. The commutator of Pi and Qj is delta Ij, just this. So the standard Hamiltonian construction, we have Hamiltonian like this. You have this standard Poisson structure, and then you introduce the equation of motion by Pi dot is equal to minus dH dqi qi dot dH dP I. That's this. Okay. So now we're about to generalize this to, I quite forgot to say that in this case, this Lax representation allows us to find the Liouville-integrable system of first integrals or an involution of this system. And namely, we can take traces of powers of L, and then it is almost evident that they are first integrals of the system. It takes a little bit more time to show that these L, that they are actually an involution. I'll probably prove this a little bit later today, just in a few, probably in a couple of, well, not in a couple of minutes, but probably in 15 minutes. In more general situation, in fact. So, what is the generalization of this system? It is the naive generalization you obtain when you allow L to be arbitrary symmetric metrics. So we begin with Lax presentation. We don't start with something very mechanical. And therefore, the mechanical meaning of this full symmetric of the system is, well, it's not known so far. There are many speculations that one can relate this system to a system of points where every point interacts with every other point, but it hasn't been done yet. I have never seen this done.
But this classical one,
it stems from that classical mechanical interpretation. So, but in the case of generalized full symmetric Toda system, we have Lax presentation. We can show that it is in fact Hamilton function, Hamilton system, and I'll do this today, I think. But no mechanical interpretation is known. At least I don't know. I have never seen it. So let L now be arbitrary symmetric matrix. I can still define its naive anti-symmetrisation by the formula L plus minus L minus. That is to say, we preserve the elements above the diagonal, we delete the diagonal, and we invert the signs of the elements below the diagonal. Since the commutator of any symmetric matrix with and skew symmetric matrix is symmetric again, one can see it easily, we can consider this kind of equation. It is well defined. There is no ambiguity here. Okay. Now, again, we have an equation. It is easy to see that traces of matrix L to some powers are first integrals of this system still. But what does it mean in involution? To make sense of this word, I need to speak a little bit about the Poisson structure. So, what Poisson structure? We use. So there are different ways to do this. So let me try to reproduce the computations from our joint paper with Yuri Chernikov, which appeared in the archive a couple of months ago. It's a well-known fact, actually, but I have never seen this done accurately in any text available. So let us do the following thing. Consider the pairing. Consider the pairing on matrices, on all matrices. Let it be traceless matrices. So probably better to use this notation. A and B will give us trace of A transposed times B. So in coordinates, it is just the sum of A ij times B ij, sum over I and j. This is a positive definite, non-degenerate. Non-degenerate. Okay. Let us consider now the space. So when we have a positive definite non-degenerate, even just non-degenerate pairing on a space, we have a map from SLN to SLN star. Right? Let's take the space of symmetric matrices. Traceless matrices well, we can actually restrict our attention to traceless matrices because, as we know, trace of matrix is a first integral of the equation. Actually, it is not just first integral, it's Casimir function. Well, we will see this probably in a very short time. So let's consider, let's fix the trace. It will be equal to 0. So this is an element in SLN. Then this map induced by the pairing
Symmetric with zero trace, yes?
Yes, symmetric with zero trace. I want to put it into SLN. It will send it to, well, to something. Okay, some subspace. In SLN. Star. It is easy to see that this pairing between symmetric and, say, the space of upper triangular matrices is non-degenerate. Hence, we can identify using this map symmetric matrices with zero traces with B and B plus upper star. And I'll use this identification, to pull the Poisson bracket from here, the canonical Poisson bracket on the dual space of a Lie algebra, to the space of symmetric matrices. That's what I'm going to do.
Canonical Kirillov constant.
Canonical Kirillov constant. Namely, so it means that if we have two functions, f and g, on symmetric matrices, real symmetric matrices, let it be real once and for all, then we have the following formula. F and g, and you can calculate their commutate their Poisson bracket at the point L. Will give you the following thing. First, you take L, then you take the how do you call this? It's denoted by nabla, but that's gradient of f and g. Gradient of f and f of g. And I take the gradient of g as well at this point. Well, this is a symmetric matrix, dual space of symmetric matrix. But then I use the projector from symmetric matrices to upper triangular matrices, the M bar. Take the same M bar here, and they take the commutator. And this pairing is nothing but that, but what I told you.
This is exactly the pullback.
Yes, this is precisely the pullback of this from star. You see, because the pairing is just what is this pairing between symmetric matrices and upper triangular matrices? It is just when you take L and you cut it into, well, take the upper half of it and take the usual pairing, the same pairing as we had before, with upper triangular matrices. Yeah, just this. So L just goes to L plus, maybe with some coefficient, but nothing else.
What is M bar? M bar.
M bar is a projection from symmetric matrices, actually from SLN. We have projection to upper triangular matrices. And along the orthogonal matrices, because you see the annulator of symmetric matrices here with respect to this pairing is orthogonal matrices, are orthogonal matrices. You see? And therefore, this M bar is just a projector in this decomposition from SLN to B plus. M bar. So it's just this projector, and it is alone SON because SON is the annihilator of symmetric matrices in this pairing. And we just, it's a kernel, so we can just project it in a well-defined way. But this actually will earn us some coefficient here, but we can either erase this coefficient and work with it. We don't care much about it. It doesn't change the nature of dynamics. So we have this Poisson structure. Actually, I can continue. I can change this formula a little bit, because in addition to this projector M bar, I have projector M from SLN to SON along B plus, right? So that M bar plus M is equal to identity, right? So let us do this. Let us change this a little bit. What is it equal to? It is equal to L commutator of 1 minus M of nabla F, 1 minus M nabla G, right? Now I expand it, and what I get is L. Now there are 4 terms here. The first term is the commutator of nabla F and nabla G, but nabla F and nabla G are symmetric because they are functions on symmetric matrices. So, and commutator of 2 symmetric matrices is skew-symmetric. So the pairing of symmetric and skew-symmetric is 0. We don't have it. Then we have L pairing with M of nabla F, M nabla G. It also vanishes for the same reason, because these are skew-symmetric, their commutator is still skew-symmetric, so it vanishes as well. And in the end, we have 2 more terms which actually are important, which we can take care of. And that's L nabla G M of nabla F plus L G nabla G M nabla G nabla F. So this is the formula, but just let me make just one small remark. Here, when I use this nabla, I mean the gradient, whatever it means, in the sense of symmetric matrices. Because if F is a restriction of some function F tilde from SLN to symmetric matrices, we can speak simultaneously about the symmetric gradient of F and usual gradient of F tilde. And they need not be coincide, they need not be the same, actually. They can be different. They are the same if and only if this function F tilde is invariant with respect to transposition. F tilde of X transposed should be equal to F tilde of X. In that case, you have the same, but in general, they're 2 different. So this formula works for symmetric gradients. I use this fact that they're symmetric, right? And this also works for the symmetric gradients.
Symmetric gradient.
Well, it's symmetric of a function as functional as symmetric space, gradient of differential of the function. So it's symmetric matrix in some sense. It is kind of, so symmetric matrices, they have coordinates aij, and basis with respect to the basis eij. So eij is the matrix unit plus eji. So with respect to this basis, I have nabla f is just sum df daij multiplied by this. Maybe with 1/2, I just don't remember this. Just this, up to 1/2, which I omit. Okay, so I have this formula. Now it is not very hard to show that if f and g are restrictions onto onto symmetric matrices of trace functions, and they are in evolution. Namely, if we look here, for instance, we'll see that, in fact, these functions verify the condition that trace of Lk is equal to trace of L transposed K, right? For any matrix L, right? So in this case, we don't care whether we have symmetric gradients or usual gradients. So on the other hand, nabla, but now if this is the usual gradient of G, and G is invariant with respect to conjugations by anything. So if G is invariant with respect to conjugation, then this is equal to 0.
Independently of f.
Independently of f. Actually, it's kind of it's due to the following formula that if we take the action, let's consider vector. Let's fix this vector. So this vector. There is L here, but let's fix once for all this vector. We have vector field on matrices, in fact, on matrices, on SLN, given by conjugation with this vector, with this matrix. Namely, it is kind of, if this vector is psi, and we can take exponent of t psi, take a joint action by this exponent, apply it to function g, right, of anything, of L, of something. Then d dt at t equal to 0 of g, like this, will be equal to L Actually, it should look like this. It should look like nabla G L this vector psi on one hand. So this is 0, of course, because G is invariant with respect to a joint action, right? But on the other hand, we have this formula using the symmetric properties of this pairing, since it is actually invariant pairing in the sense of Lie algebras and B groups. I can push this psi from right to left or from left to right, doesn't matter, and get precisely this term. So it means that in this case we have the same thing. It is important that here there is no difference between symmetric gradient and usual gradient of the function. And that's true because it verifies this condition. And the same goes for here, the same is true here if f is also invariant of this sort. So this actually proves that these functions are first integrals and involution of Toda system. I quite forgot to say that if I take the function trace L squared again, then an easy exercise is to show that the equation of motion with respect to this is given by precisely the same equation as before. Is L dot equal to M of L. It actually follows from this condition here, from this equation, right? Because what is the equation of motion? We have kind of L here and trace L squared here, right? Now, nabla of L is just a constant metric, so there is no problem. It just vanishes. And the only thing which survives is this. Then we push M nabla of this function to the left, and we get this equation, right? Push it to the left using the invariant properties of the pairing I used. So it means that, in fact, that the Hamilton, more generally, one can prove that the Hamilton vector field of an invariant function with respect to this Poisson structure is given by something like this. If we have an invariant function, not just invariant, actually B plus invariant function. If you have just a B plus invariant function, then its Hamilton vector field is given by the commutator M nabla F in the usual sense. Nabla not in the symmetric sense, but nabla in the sense of the full space of matrices with L. It's a Hamilton vector field. So we see that the system I was talking about is in fact Hamilton, and it has n first integrals in involution. But now it is not sufficient. This number of integrals are not sufficient for us to speak about the integrability in Liouville sense, for instance. Because, in fact, the dimension of the space on which we live is proportional to n squared divided by 2. So there are lots of first integrals we lack. Yeah, dimension of symmetric matrices is in fact equal to n minus 1 divided by plus 1 minus 1 This one comes from the condition that I assume that the trace is equal to 0. I have to subtract 1 to make sure. So it's proportional to n squared divided by 2. Even if I take into account some Casimirs, I will need still about n squared divided by 4 first integrals in involution. To make sure that it is integrable in some sense. And to make sure well, there exist different constructions of such first integrals. They all amount to the following consideration. Let's look again at the formula for the Poisson bracket. Fg is equal to L m bar nabla F m bar nabla G. And this nabla is symmetric in general, but if F and G are B plus invariant, I can show that there is no difference between symmetric and usual gradient in this case. One can replace as far as I can remember, right? Okay. Using this observation, we can show the following. We can prove the following lemma. If F and G are B plus invariant, then the Poisson bracket of their restrictions onto symmetric matrices is equal to the restriction of these two functions on SLN. So we take the Poisson bracket on SLN and restrict it to symmetric matrices. In other words, in this case, up to the sign. In this case, taking brackets commutes with restriction up to the sign. In particular, if F and G are in involution on SLN, then they commute when restricted to symmetric matrices. So I can prove this. I think it is just this B plus invariant. It follows from the same idea we have here. You see, because so this is projection to M plus, to B plus. This is a projection to B plus. If I erase this here and erase symmetric here, I can use the same observation to prove that this vanishes, that this thing vanishes. So in the end, we just have, in the end of the day, we will just have the commutator of nabla F and nabla G. And there's just a restriction of F and of the Poisson bracket to symmetric matrices. It's just the same the same trick I used before, but now, well, the sign is earned throughout if we follow these manipulations well accurately. Then there will have the sign because this is 1 minus something and so on. Okay.
Yeah, it is one minus m.
Yeah. And therefore we get this sign. Okay. Nice. So this gives us the following idea to construct first integrals and involutions. Yes, of course, we need to observe that the Hamilton function is given by precisely such restriction. They have an invariant function on the whole space SLN. In particular, it is B plus invariant. It is invariant with everything, with respect to everything. In particular, it is invariant with respect to B plus. So we restrict it to symmetric matrices, and then it will commute with restrictions of all other B plus invariant matrices because it commutes with everything on SLN. In fact, it is central on SLN. It stops being central on symmetric matrices, but when we using this relation, we see that its commutators with B plus invariant matrices will be B plus invariant functions will be the same, will be preserved. So it will still vanish. So it means that if we want to get first integrals and involution, we need to find involutive families of B plus invariant functions on SLN.
Yeah.
So there are different constructions one can use. One construction is, well, it's been known before. It's been known since 1984, but the proof was totally different from what I'm going to tell you. It's a construction of so-called Chopin integrals of Dave, Lee, Nanda, and Tema. Chopin integrals. They are given by the following construction. Take, yeah, just one small observation. If you know the invariant theory, then you probably remember that there are no polynomial invariants of Borel subgroups except for the invariance of the whole group SLN. So there are no polynomial invariants of Borel subgroup which are not invariants of the whole SLN. So if you want to get some new invariants, they cannot be polynomial anymore. And they should, it turns out one can actually find rational invariants in this case. Rational will suffice. So Chopin integrals are exactly the construction which give you rational integrals in this construction, in this sense. They've been known since 1984, but the proof was totally different. So I think giving some hint of the proof will be a good idea. So we need to find functions which are B plus invariant, which are in involution with respect to the usual Kirillov constant bracket on SLN. We observe that if we have an invariant function, so let f be an invariant function, just invariant, not of B plus, but invariant of the whole SLN. And if we apply some differential operator, D to F plus, to F, and then we take a conjugation of this by a certain element X, it will give us the same thing as D to which we apply this operator and which we act, which we use to act on F. So this action, a joint action on this function, amounts to the action of the corresponding X on D. In particular, all functions which we obtain from integrals. So if D is such a the punctuality of this action will be the same for all invariant functions. In particular,
I'm sorry, I missed what is D.
D is a differential operator.
Just another
Any differential operator. Operator. So when we apply a joint action to this function, to the value of D on F, then we have this formula.
This is obvious.
Obvious, of course. In particular, if D add is equal to certain character of X applied, a character of X multiplied by D, we see that the same character will show up for all functions, for all invariant functions at all, for all invariant functions. Hence, we see that D of the ratio F by G, where F and G are probably better to say not D of a ratio, but D of F divided by D of G, where F and G are two invariant functions, will be B plus invariant, will be invariant of this sort. Right? So, okay, now I can give you this operator. There are few such operators which are pretty easy to write down. For instance, take D over dx and n, 1n. It is to say I differentiate along the upper right angle variable in the matrix. Then this operator verifies this condition for all x in B plus. Namely, it's just the ratio. So namely, what we get will be just the ratio of this element in the matrix in B plus and this element in the matrix from B plus. And let's say that d dx n when we use a joint action by an element in B plus will be equal to lambda 1 and ratio of lambda 1 and lambda n times d dx 1n. Okay. Then you can go on pretty much in the same.
X is the dual basis in.
Yeah, x is just the variable. You can say it is dual basis. It's just the matrix element, which are matrix elements are coordinates in the space of matrices. Okay. So just differentiate along them. You can go on in the same way. You can take, for instance, the operator which is given by d dx1 and d 2n minus 1 minus dx 1n minus 1 dx 2n. So that's to say, I just take the operator which is equal to the minor of this algebraic to the determinant of this kind of matrix. It verifies the same condition. It is also invariant in this sense. Now we need to find. Now it remains to find functions f and g, which will such that d of f will commute with d prime of g for such operators. And then we can use this construction to get b plus invariant functions which will commute. So such functions exist. For instance, we can take f and g to be coefficients of the characteristic polynomial. Well, one can show that in this case, these two elements are somehow proportional. So what we get will actually be equal to just the iterations of the form d dx1n, d dx2n minus 1, and so on, d dx k n minus k plus 1. So to say, we cut out this anti-diagonal, right? And they will commute because these operators, they appear from the argument shift operator with respect to the matrix 1 t square t n minus 1. So if you shift my function, my matrix, my function by this, then I get, due to the argument shift method, a series of commutant elements. But since it will be commute for all t, for all values of t, so they actually will commute. It will give us that these operators f, where f are the coefficients of the characteristic polynomials, will also commute, and they will also be b plus invariant if I take their ratios. So that gives us some example of first integrals in involution, and they are the Chopin integrals, precisely the Chopin integrals, due to the Dave, Lee, Nanda, and Tame. Okay. In fact, if you forget about involution condition, you can just speak about all functions which are b plus invariant, and that will give you the super-integrability property of the Toda system, because the number of such functions is large enough to verify.
Yes, it's quite.
Yes.
They will be not involutive.
Not involutive. So that's what they call.
And still it is called super-integrability.
I think it is either super-integrability or non-commutative integrability. I don't remember if there is some difference between.
Never mind, it's just words.
They're just words, but actually you can speak about non-integrability of function with respect to the system of first integrals, which are not in involution, provided that there exists some inside this system. There exists some integrals in involution, and the remaining part of the integrals, even if they're not in involution, are still large enough. That's what they call non-commutative integrability or super-integrability, I think. Okay, but now I'm going to speak about the integrability of the system in the sense of Lie-Bianchi theorem. So let me recall the formulation of Lie-Bianchi theorem as much as I can remember it. So suppose we have an integrable, a dynamical system x dot is equal to x of x, where x is a vector field on an n-dimensional space. Vector field. Well, I speak about the first order differential equations. Of course, one can speak about other orders, but this is probably a more convenient way for me, at least. Is a dynamical system on, well, locally it is always on Rn, so we can assume that x is in fact x1 through xn, and x capital is also x1 through xn vector field. A symmetry, an infinitesimal symmetry, of the system is any vector field y on Rn, also local, such that the commutator of x and y vanishes. Now, Lie-Bianchi theorem says that if you have a sufficiently large algebra of symmetries, Lie algebra of symmetries, which is resolvable in the sense of Lie algebras, then your system is in fact integrable in quadratures, in the sense of that you can find an iterative process consisting of taking integrals of certain functions and substituting functions into themselves, into other functions, so that in the end you'll get the solution of your system. Namely, you need an n-1 dimensional Lie algebra G of symmetries of Rn, local symmetries, such that its action on Rn is locally free. In the sense that the span of tangents, the span of the values of vector fields in this algebra plus the vector field x will cover the whole Rn locally. Yeah? Span of y1 through yn-1 x at the point x is equal to Rn. And this Lie algebra G is resolvable. Then the system is integrable in quadratures.
Why resolve?
Huh?
Why not solve?
I don't remember. Is there a difference between these? Okay, solvable. Okay, solvable. I don't remember the difference between these two terms.
So you just solve it.
Solvability. And what is the difference between
I
solvability?
don't know.
I have no idea.
I know what to solve.
I thought they were They were synonyms, but okay, solvable. Then the system is integrable. So let me briefly in quadratures, yeah, in quadratures. Let me briefly recall. Let me briefly give the construction. I think I'm running out of time. How much time do I still have? I have 30 minutes at least. I'll need 30 minutes to give this construction. They have 30 minutes.
Yeah, you do.
Okay, nice. So let me give the construction of such Lie algebra in case of the full symmetric Toda. Or full symmetric Toda. So to construct such system of symmetries for full symmetric Toda, what I need first to transfer it from symmetric matrices to the group SON. Namely, it is clear that the evolution of my system preserves the spectrum of the system. So let us choose a spectrum of L. Yeah, of L. Let us choose an orthogonal matrix and a diagonal matrix L, lambda, such that L decomposes into such product. Psi is orthogonal. Lambda is diagonal and real. Such decomposition always exists. Moreover, it can be chosen in a unique way locally. It is unique if we fix the order of the eigenvalues of L. For instance, we say that they grow. And also, we need to choose kind of, when we fix this order, then the solution will be up to multiplication of psi by a diagonal matrix with plus and minus units on the diagonal. Right? So we can fix, so this is a discrete series of solutions, so we can just fix one of them. And so locally we'll have this unique decomposition. So instead of working on asymmetric matrices, I'll work on SON. And on SON, I can define a vector field which will play the role of Toda system. So the Toda system on symmetric matrices is induced on symmetric matrices is induced by the following vector field on SON. Namely, I will denote this field by T sub lambda. Lambda is this matrix. Lambda is this matrix. And at the point psi, it will be given by the projection onto orthogonal matrices of the joint action by psi on lambda. And then we need to translate it back to the same point by multiplying by psi. Okay. it is easy to see now that if psi of t is an integral curve of this vector field t lambda of psi, right? Then L of t given by the action of psi of t on lambda, psi transposed of t, psi transpose of t, will be a solution of the Toda system. Moreover, due to the uniqueness of this decomposition, if I have a symmetry of this vector field of t lambda, right? If I have some symmetry here, I can pull this symmetry to the space of symmetric matrices in the same way. I just take the solution of the same, take the integral curve of this vector field, right? And then I use this integral curve to move along the symmetric space of symmetric matrices. And it will give us a symmetry of this field here on symmetric matrices. Okay? So now I'm going to construct symmetries of this vector field. So from now on, I'm working on the space of symmetric matrices on the group SON, real group. So first of all, I'll prove the following proposition. Let X be in any matrix in SLN. Let X be any matrix in SLN. Consider the vector field Tx given by the same construction. I take the joint action of psi. Psi is an element in SON. Apply it to X and take the projection onto skew symmetric matrices along the space of upper triangular of lower triangular matrices, right? You remember that M is the how do you call this? The complement projection of M minus of M bar. So this is projection as SON. This is a projection of B plus or B minus. I don't remember already. I think it was B minus, but maybe it was B plus. Okay. Then the commutator of two vector fields, Tx and Ty, will be equal to T of X and Y. I mean, this is just the commutator in SLN. In other words, these vector fields give you a representation of the Lie algebra SLN by vector fields on SON. Let us prove this. It is very easy and very interesting in my opinion. So the proof is based on the following two formulas. First formula. Since M is a projection with respect onto a Lie subalgebra, with respect to another Lie subalgebra, M verifies the so-called Nekhoroshev condition, just to say M square of the commutator of X and Y minus M of X, Y minus M X, M of Y is equal to the commutator of M of X and M of Y. That's the first condition. It follows just in one line from the condition that M is a projection onto a Lie subalgebra along another Lie subalgebra. That's the only thing we need. The second condition, the second formula, is again quite simple. And it says that if you have a vector field X on a Lie group G, which is given by the formula X of G is equal to some small x of G multiplied by G. That is to say, we have a smooth map from G to the Lie algebra, to its Lie algebra, G, right? This is a vector valued function on X. And we use the translation, the right translation on G to pull all the vectors from the origin, from the unit of the group to any point, any given point. Then we have the same formula for Y, where instead of X of G, we use Y of G. Then the commutator of X and Y is given by Z of G times G, where Z of G is the combination of the Lie derivative of Y of G with respect to the vector field X minus Lie derivative of X of G along the vector field Y minus the commutator of X of G and Y of G in Lie algebra, in the Lie algebra. It's just a very straightforward formula.
Yep.
Very easy. I couldn't find it in textbooks, so I had to prove it. But now if I combine this, and we also remember that when you differentiate the joint action, you get the smaller joint action. You will get precisely the combination of this, and this here on the right. So what we get is vector field induced by the M square of the commutator add psi x add psi y. But this square can be erased because this is a projector, so its square is equal to itself. And a joint action is the homomorphism of the algebras.
You mean that any if you have an arbitrary Lie algebra,
yeah,
and you have a projection of this algebra along
another Lie algebra,
then
you have this. You have everything.
Yep.
Yeah. You just have this. You have everything. All this works for any pair of Lie groups and Lie algebras. You always have this representation by vector fields. When I talk to people, they would always try to tell me that this is what they call Dressen transformations. I couldn't see this. I tried several times in several accounts of Dressen transformations, but they all seemed similar but different. Seemed very somewhat similar but different. So I have never seen this formula before, but well. Okay. So first I have this, now I have this collection of vector fields, and I have this commutation relation. In particular, the Toda field, the T lambda, is the field which I associate in this way to a diagonal matrix. All diagonal matrices commute with each other. So I see that Toda fields for different lambdas commute with each other. That's it. Unfortunately, if I just take arbitrary x and I try to commute it with t lambda, tx with t lambda, I don't get 0 in general. For instance, if x is the matrix unit, then t lambda commuting with t eij will, up to the sign, be equal to lambda I minus lambda j t eij, right? Because of that commutation, because this commutation relation holds for lambda and eij, just this. Okay, I need to do something with this vector field to compensate this factor. And this is done by multiplying t eij by certain function f for which t lambda, on which t lambda acts by lambda j minus lambda I f by this formula. Okay, I can give you this construction in general situation. It involves looking for certain representations of the Lie group SLN, of a Lie algebra SLN more generally. And then using these representations of SLN, I can produce such functions in in industrial scale, so to say. But the simplest thing I can do, I can just take f to be equal to the ratio of psi. So it depends of psi. So it'll be equal to the ratio of psi and I divided by psi and j.
Gosh, do you need eigenvalues to be pairwise distinct?
No.
They may be.
They may be arbitrary. All right. So the distinction between eigenvalues is necessary to make sure that this is in one-to-one relation with whatever happens on the level of Lie or on SLN, sorry, on symmetric matrices. Right, but so far, but now when I work on SON, I don't need this assumption in it at all. There is no, I don't need this assumption anymore. It is just pure algebra now, differential geometry, a little bit of differential geometry. So if I take this f, and the claim is that I have this condition, so this vector field will now be in very symmetry of the vector field T lambda. So I'll denote it by Tij. This product will be denoted by Tij. And I have the condition that T lambda and Tij commute. Oh. We're almost there now, because now I'm going to show that these vector fields, Tij, somehow they do not form solvable algebras themselves, but they contain solvable algebra. Inside these vector fields, there is a solvable. They're all symmetries. They're all symmetries of the vector of T lambda. So I'll find, and yeah, and I also quite forgot to say that in the generic point on SON, these vector fields span the whole space. So Tij span for I less or equal to j, span TSON in the generic point psi. And that's almost clear because you need to check it for Eij. They have the same span in the generic point. And yeah. So I just only need to show that there is a solvable algebra inside these vector fields. The remarkable thing about it is that if I take the commutator of Tij and Tkl, it will be it can be expressed in terms of Tij and Tkl again. I don't need any new vector fields here. It is the space of these vector fields is closed under commutators. The formula is a little bit tricky. It doesn't recall. It doesn't resemble anything familiar. I'll try to restore it. It is something like delta jk minus delta jl t this t I think it's kl minus delta li minus delta lj t kl ij, and the remaining part is just the commutator in the GLN group. So it's delta jk kj t I l minus plus delta k I l t k l kj.
Yes, this is more or less clear, yes.
So if you look here now, if you look at this here, now there are different ways you can now earn the solvable Lie algebra. One way is what I myself personally observed, is that if you take the difference, if you take the upper triangular part of this space, you take the difference between T, I, J, and T, I. So I is the number of J minus 1, J, right? The difference of these two. Let's denote this difference by P ij. Then the commutator of P ij and P ik will be equal to 0. So when they are from the same column, they just commute. And the commutator of P ij and P lk is I don't remember what, but it belongs to the column with which is farther to the right. So let L be greater than I, then it belongs to the column span of P L S. So this gives you,
So you will,
yeah, and finally it will be resolvable. Solving will be solvable.
else.
It is not sufficient. You just to make it work, you need to add diagonal elements here. They commute with everything, which is more or less clear because everything commutes with T lambda for all lambda, for all possible lambdas. So you add this diagonal part, and then you get precisely the dimension you need, right? A more industrial way to look onto this is due to Dimitar Lalaev, who observed that this algebra is isomorphic up to a central extension to the Lie algebra of matrices which preserve the vector 1, 1, 1, which vanish on this vector. So in some sense, it is a subalgebra in GLN, and hence it has solvable part coming from the intersection of this subalgebra and the upper triangular part of GLN. That's all.
Okay, this is all for today.
Yeah, it's all for today. If the next time I'll speak about some a bit different topic, I'll speak about deformation, quantization, and
Yes, we know.
yes, and but if you have questions, I can answer them
We shall answer.
next time.
Okay, thanks a lot. Questions, remarks? Well, it was a very clear exposition. No remarks, no questions. Okay, thanks a lot. So we shall have a continuation in 2 weeks, and the next time there will be talk for Kostya Drushkov.
Mhm.
Okay, thank you, and see you in a week. Goodbye.